In this video, I'll be helping you with the ALEKS problem type called graphing an ellipse centered at the origin ax squared plus by squared equals c. And before we jump into this example, we'll take a short detour to look at the standard form of an ellipse and its different parts. All right, this is a short sidebar to talk about the parts of an ellipse that you're going to be asked to calculate. And before we look at an ellipse, I would like to start with a circle and then see how that turns into an ellipse. We have the standard form here for our formula of a circle, x minus h squared plus y minus k squared equals r squared, where hk represents the center of a circle, and the r that's being squared is the radius from that center. An ellipse is similar to a circle, except that it appears to be stretched. And from the standard form of an ellipse, we can see that it still has that center, hk. However, the stretching occurs as a result of being divided by a squared, which gives us the length from the center out to the ellipse, which we can see here as a, the square root of a squared, and b squared, which is similar, but the distance from the center in the other direction is b. But notice it's still addition, and that where we did have the radius squared, an ellipse will always be 1. I would also point out that the a and b are always chosen such that a is greater than b. And you can see in this example that the a squared is under the x term, so it has been stretched horizontally. If the a squared was under the y term, then the ellipse would be being stretched vertically instead of horizontally. But for this example, I'll keep it horizontal where the a term is under the x value. For terminology, a is the major axis, so the length of the major axis is 2a, and b is the minor axis, which has a length 2b. Along the major axis, we also have the foci, which is the point c, where c squared is equal to a squared minus b squared. And this is important because c defines the ellipse, since any point on the ellipse has a distance to the foci and a distance to the center. The sum of these two distances for any point is always the same. Okay, so with that standard form in mind, we'll now turn our attention to this example, which is clearly not in standard form. The first thing we must keep in mind is that for standard form, this constant side must be 1. So to correct for that, I'm going to divide both sides by 9. And that means on the left, dividing each term by 9. That gives us x squared over 9 plus y squared. And since we want to see these denominators for standard form, I'll leave that over 1. And our right-hand side is 9 divided by 9, so 1. Recalling that this is our standard form, where the a squared is the larger of the two denominators, here it's underneath the x, I'm going to rewrite this one more time just to show all the pieces in standard form. The x squared would be x minus 0 squared. And since that denominator should be written as a perfect square, I'll write 9 as 3 squared plus the y squared would be y minus 0 squared over, here again this is b squared. Since we only have 1, we can say that that is 1 squared equals 1. And we can see from this form that our h and k are 0 and 0. The center is at the origin as the description indicated. So our center is 0, 0. The stretching occurs in the x direction is our largest axis. My a is 3, so I would go 3 units in the x direction from the center in both directions. These points would be on the ellipse. And then in the y direction, that length is only 1 unit. So I would go from the center up 1 or down 1 to reach the ellipse. And now with these 4 points on the ellipse, I can sketch out the graph of that ellipse. And again, we got here by going 3 units left and right of the center and 1 unit up and down from the center.